Good morning, students. So today we will start with the Matlab simulation of DC to DC buck converter. So this will be our first simulation experiment. So we are going with Matlab. We can also use PSpice also. So here we are going predominantly with Matlab. Since most of you are familiar with Matlab, we will be using Matlab's simulation software. So you know that a DC to DC buck converter is a step down converter. What does that mean? That is, the output voltage will be less than the input voltage. So you know that this will be the output voltage V naught, and this is the diode D1 here. So rest everything is marked here. So before going into the simulation, I will give you just a small theoretical idea. I will give you, even though you have learned already, I will give you a small idea. So DC to DC buck converter means the output will be less. That is, the input voltage is bucked or is lower to a lesser value. That is the case. So in case of a DC to DC buck converter, there are two modes of operation. So you know there is a switch S1 given. So in case of a DC to DC buck converter, there are two modes. One case when switch S1 is on, and the second case when the switch S1 is off. On condition and off condition, how does the circuit behave? That's we are seeing. And you can also see that the switch that we use, it can be an IGBT or it can be a MOSFET. So most of our simulations and hardware implementations we go for the MOSFET switch. So there are many reasons for that. So now I'm not going into that. And L and C, the inductance and capacitance which we are using here, they are actually used for filtering, because the output voltage or current that we are getting, the inductor current and inductor voltage, everything, the capacitor voltage and all, we are getting, will be having ripples. So in order to filter the ripples, we use inductance and capacitance. Inductance for current and capacitance for voltage. So then coming to the two modes of operation, which is when switch is on and switch is off. So we can see that this is actually the circuit for buck converter, you know it, right? So what actually happens is when in the initial condition, when the switch is on means this is a closed circuit. So the voltage, positive half cycle voltage will come here, and but when it's reached the diode will be reverse biased. That means this will act as an open circuit, and this way the circuit will be completed. So inductor, the energy, the voltage will get stored in the inductor during positive half cycle. That is when the switch 1 is on, and not the positive half cycle when the voltage is coming. Actually, it's a positive voltage. And in the next half cycle, when the switch is open means this entire circuit will not come into effect. That means the stored voltage in the inductor will be just circulating like this. Okay, so this detailed figure again, I have put it here. During on condition and off condition, what actually happens. So this is the on condition. You can see during on condition, the red color highlighted part is only coming into effect during on condition. So the source voltage will be there, then you will get the output voltage. Inductor also will be getting charged. During the during the S1 off condition, when the switch is off, the the voltage stored in the inductor during the first half cycle is getting released. And so this is a forward bias condition only. The diode will be forward bias, and this the voltage will be circulating like this. And here the current will be circulating like this, and here this will be the condition. So this is the on state and this is the off state. So during the on condition, we can write, like, if this is the voltage VL, we can write by KVL, we can write as a Vs is equal to VL plus V naught, and if this is Vc, then Vc is approximately equal to V naught only, because they are parallel. During off condition, so this is VL, this is V naught. During off condition, and we can mark the current also. This will be IL, this will be IC, and this will be I naught. Then what will be the value of current? then the current IL can be written as Kirchhoff KCL. If you're writing KCL, then the current IL will be IC plus I naught, and VL will be equal to minus V naught here. So only because only this circuit is coming into effect. So I think so far whatever I have discussed, you understood. This is a circuit. This is the same circuit which we need to develop in Matlab. Now we are going into the design of the DC to DC buck converter. And also I will discuss about the waveforms also. So switch on condition and switch off condition. When the switch is on, what will happen? When the switch is off, what will happen? So this switch is on, this is the KVL equation, and when switch is off, this is what actually happens. Now we will see how the inductor and capacitor waveforms behave during on and off condition. So let's consider the waveforms. So initially we have the source voltage. This is DC source voltage. So this is Vs, some value. And then coming to the source current. You know that the source current is available only during the condition when switch is on. So here we will mark the axis, x-axis T on and then T. You know, T on means when the switch is on, and then T on plus like T off will be the total time taken. Okay, you know that. So they are all linear elements. So inductor current will be, the source current will be increasing like this during the on condition. Off condition means source current is not there. Same way when the switch is on again. So this will be the source current. Now come, so this is the source current IS. Okay, this is the source current. I will mark it here also. This is the source current. Now coming to the inductor current IL. The inductor current IL. What will be the inductor current IL? So you know that the current is flowing through the inductor during on condition as well as the off condition. What happens? So in the on condition, the inductor is getting charged, and when the switch is off, the inductor is getting discharged. So same way this will be charging, and here it will be discharging, and again it will be charging. Likewise, it will go on and off condition. So here we can mark that this is the value of IL minimum, and this is the value of IL maximum. And then what will be delta IL? Delta IL is the ripple current, that is IL maximum minus IL minimum. If we are giving I1, I2, it will be I2 minus I1. So in order to remove the ripple, we use the filter components. You have it already have it in your circuits, capacitor and inductor. So we got the inductor current. Now we'll talk about the output current. How you will get the output current? During on condition and off condition, from the circuit you can see that output current is there, right? Here you can see output current. Here also current will be flowing. Here also current will be flowing during on condition as well as the off condition. So it will be a DC current only during on condition as well as the off condition. The output will be a DC current. So we represent that by using a straight line DC value. I'm not going much into the details. You can always check the equation, how the equation it will behave like, because I have already written the equation here during on and off condition how it will behave. Now coming to the capacitor current, how the capacitor current will behave. So I will again mark T on here, and I will again mark T here. So you know that the capacitor current IL will be equal to IC plus I naught. That means IC is equal to IL minus I naught. That is inductor current. So you have both IL you have, I naught you have. So there can be a condition when IL is 8 volt. I consider IL is 8 volt and I naught is 5 volt. Sorry, IL is 5 volt and I naught is 8 volt. That means in that case IC will be minus 3 volt. That means that it will start from a negative value. So this will go like this. Then again it will come like this. Then again during augmentation. So here we can say that this is the charging area and this is the discharging area. That is the capacitor current. Now we will move on to the capacitor voltage. Capacitor voltage. So you know that it should be that is approximately equal to the output voltage itself. So that should be a DC voltage, right? Buck converter means it should be a lesser value. Based on the duty ratio, you will get it. But because of this behavior of capacitor current, the output voltage will not be a pure DC. When you do the simulation also, you will understand. It will be a pulsating voltage. It will be a pulsating voltage. Actually, based on these spikes only we are getting. Based on the inductor current only we are getting. It will be a pulsating one. So in order, so this will be having a maximum value as well as minimum value. That means there will be a delta VC value. So actually, these waveforms from these waveforms we obtain the value of designed value of inductance and capacitance, because we consider the ripple, because you know that the value of inductance and capacitance, what why we are using for to remove the ripples, right? So based on the ripple factor delta V naught by V, such thing, such values we design the capacitance and inductance value. Okay, so now we will see how we design the values, like the formula for designing a DC to DC buck converter. When it comes to the design of a DC to DC buck converter, so let's consider one condition. We have given a source voltage of 48 volt. We need to obtain an output voltage of 15 volt. The switching frequency is given as 40 kilohertz. So time period we should take as 1 pi frequency. Then we have the output resistance, that is the voltage side. We have output voltage, we have 8 ohm. So initially we calculate what is the duty ratio. So I have already written everything here. So duty ratio will be V output by V input in case of a DC to DC buck converter. So 15 by 48. So the duty ratio will be 31.25 percentage. And when it comes to the value of inductance, we calculate L minimum is equal to 1 minus duty ratio into resistance by 2 into frequency. So duty ratio we have, resistance we have, frequency also we have 40 kilohertz. So we calculate it as 68.75 microhenry. But actually, when we are doing the simulation or the hardware implementation, we assume the value of inductance to be 25% larger to have a continuous conduction. In that case, the value of L minimum will be 25% more. So 25% more means it should be approximately equal to 85.93. The exact calculated value is 85.93. And when it comes to the capacitance, you have the equation. So as I explained during the explanation of waveforms, there will be a ripple voltage. So we consider delta V naught by V naught, and that approximately we take to be delta V naught by V naught, we approximately consider as less than 5%. So this is the calculated value of capacitance, 125 microfarad. So inductance and capacitance both we are using for filtering of the ripple current as well as the ripple voltage. Now we will move on to the Matlab simulation of the DC to DC buck converter. I hope that up to whatever I have discussed now, the circuit, the switch on condition, switch off condition, the waveforms, that is the input voltage, output voltage, source current, inductor current, then what else, capacitor voltage, capacitor current, everything is clear for you. Now we will move on to the Matlab simulation. So initially we should switch on Matlab. So whichever version you have. So here you should go to new. Then you should take a Simulink model. So it will come like this. Then you should go to the library. So here whatever you need, the DC voltage source, DC voltage. So DC voltage source from here you can take. You can add block to the model like you can give. So then it will come there, and then whatever things you need, MOSFET switch will be. You can just write it down here, MOSFET, or you can write on the screen, Simulink screen itself. So whichever way. So conventional way I am teaching you. So MOSFET also you can take. Likewise, you can take all the elements. So what all will be there? MOSFET will be there, switch will be there. Then diode will be there. Then so diode also you can search like this. So this diode we will take. Okay. Then this power guide block should be there for simulation. Power guide block. Also you should be searching like this. Power guide block, and then we have the RLC. RLC also you should take. So RLC block we will get. So we take this one, the series RLC branch. Series RLC branch we take. Okay. And block 2, the same way we will do. So now, and after that you can do the connection. So when it comes to the series RLC branch, so you know that we need a capacitor in parallel, then output resistance, and inductor in series. So what we do is we just keep it like, I will make one copy. For copying, just same way, copy and then paste. So you get it like this. So R means R you should select, apply, okay. Same way inductance means L you should select, apply, okay. So this is the way. Okay. So now this circuit I have obtained, like this is the DC voltage source, the switch which is the MOSFET, then this is the diode, then series RLC branch. So this is the capacitor. You can change the name also, capacitor. Then the load resistance, don't begin this load resistance, then voltage measurement. So all these blocks, there's like exactly this name you type in the Simulink library, you will get it. So if you type a wrong spelling means you will not get it. Okay, so be careful. Then scope, then RMS value also we can measure. Then this power gate block should be there. So I will give this one here, and then I will start simulating. So this is how we simulate. So input voltage also I have set. I will show you these parameters. Input voltage 48 volt, our design voltage 48 volt. Then inductance value 85.93 microhenry. Then capacitance which is 125 microhenry. Then resistance which is 8 ohm. Then the pulse generator we have. So this 2.5 10 raised to minus 6, like 2.5 10 raised to minus 6 second means actually it is 1 by the switching frequency, 1 by 40 this value. And pulse width duty ratio we obtained at 31.25%. From the design you know all these things I've already explained. Then from here we can measure the inductor current also, everything. Okay, so out of all the 7 waveforms I am not obtaining here. Here I am showing you only the input voltage, output voltage, and then the inductor current. Other voltages you should obtain. That's your homework. Okay, so now I will run the simulation. So this will be happening like this. I already run it one time, so this is happening first. So likewise it will show. You should have a better configuration. Actually my laptop is 8 GB RAM, so But 4 GB is enough. 4 GB RAM is enough. Things will be more easy for you if the RAM is better. You can try to do this online also. Okay, those who don't have Matlab, you can try to do this online. So we have reached 42%. So it's just slowly. We have given only up to 1, so it will not take much time. So from here you can see the display. So approximately it is coming 14.37, the RMS value. Okay, so it's almost done now. Yeah, it's done. 100% now. So now we'll go to the scope value. You click here. So you can see that we have obtained, we have given an input voltage of 48 volt and the output is approximately 14.442, 14 point, that area, RMS value. Because we will not obtain exactly, we will not exactly obtain free. I will show you a better view. So you can see that exactly how we obtain, because this is actually due to the ripples delta V, so this is how we obtain 14.42, and this is the inductor value, inductor current also it is given. Scope number 3 is inductor current, right? Yeah, inductor current. For a particular designed value, we have obtained these things. I hope it's clear. So these are drawings you should draw in your rough record. In your record, exactly these values, and you should upload the same, the obtain the snipped values you should obtain. You should make a file online, have soft copy, and you should upload it. I will tell you in detail. So I hope this is clear for you. Thank you and have a nice day.